We'll come back after the very short break. Um, and our next speaker for this third and final session today is Dr. Sukhendu Ghosh. So, Sukhendu is working as an assistant professor in the Department of Mathematics, IIT Jodhpur. He finished his PhD and Masters in Mathematics from the Department of Mathematics, IIT Madras, and then he briefly worked as a postdoc in ULB Brussels and also a couple of jobs in between. So he'll be today talking about linear stability analysis of some complex flows, and his research interest includes hydrodynamic instabilities, mathematical modeling, and Lie group applications. Over to you, Sukhendu.
Yes, so thank you so much for this introduction and very good evening to all of you. So, as Satyajit told, actually, I'm going to discuss about linear stability analysis, some complex flows. So, basically, I'm interested to discuss about some hydrodynamic instability of stratified flows, so which is one kind of complex flows. So before going to the details, let us start with a few fundamental things, means how actually linear stability or hydrodynamic instability works and where we can see such kind of instabilities, how we can handle such kind of instabilities and related applications. So if we start with a very simple question, what is hydrodynamic instability? Then I can tell that this is a mathematical approach which you can apply to different flow system to capture the behavior of a flow system in different stage. Now, how we can check stability or instability of a flow system? To check that, we have to understand different stage of a flow system. Okay, how stages are changing due to some external effect or internal effect. All those things we need to understand. So, if we start with a very common example of tap water, so which is given in figure 1, then it will be quite clear that one flow system can have different stages. So like if you see figure A, then this is initially when you are opening your tap in your basin, then pressure in the water flow is less, and then your flow will be come quiet, and your streamlines will follow some patterns. Okay, so this stage actually known as laminar stage or equilibrium stage or initial stage, you can say. But if you increase your flow speed by just opening your tab little bit more, then what will happen? That shape of the water will destroy, and your streamlines, flow streamlines will behave differently, and they will not follow certain pattern. So this stage we can consider as a part of stage. And further, if you increase your flow speed, then what will happen that your streamlines will follow a chaotic situation or chaotic path, and that kind of stage actually known as turbulent stage. So therefore, in a flow system, you can think about three different stages like laminar stage or initial stage, then Patav stage due to some disturbance, some external disturbance or internal disturbance, and another stage which is known as turbulent stage. But our interest in this particular talk in the middle stage, which is Patav stage, and we want to study how this Patav stage means can go back to the earlier stage like laminar stage, or it can go to the turbulent stage. Okay, so this behavior we want to track out, and we want to define our definitions corresponding to different instabilities, and we shall apply those things for a set of problems, that stratified problems. Now the thing is where you can see such kind of instability, hydrodynamic instability, where actually there we can apply those things. So in natural problems as well as industrial problem, in biological problem, everywhere you can see such kind of instability, and this instability can have good impact or bad impact depending on your flow systems. Like if you see the second figure, I have given another picture of blood flow system inside a human body, and for this blood flow you can think about two different way the effect of instability. Like if you think about heart attack, of inside human body, then that is a bad impact of hydrodynamic instability due to the huge instability inside your flow system, that heart attack can happen. And another way, if you think about that drug delivery system, so if you are injecting some drug inside a human body, or say inside the blood of a human body, if we are injecting something, then that will transport from one place to another place due to the some instability behavior of the blood flow system, and that is a good impact of hydrodynamic instability. So with this brief idea, now let us move towards our main object, that means a set of complex problem which is stratified flows. Okay, so now the second thing is, what is stratified flow? So stratified flows is nothing but if some fluid properties are changing continuously inside your flow system in terms of space and time or any other variable. If there is a continuous change or there is a certain change inside the flow system, then that kind of systems are called stratified system. And due to that change, change in fluid properties, there will be huge change in the dynamics of the flow system as well as instability behavior. And that's why we can tell that this stratification process has remarkable effect on your flow instability. Okay. So our interest actually in two types of stratification, either density stratification or viscosity stratification. So in this talk, I am going to discuss about viscosity stratification. And again, I have given actually two different kind of flow system here, where you can see stratification, that means change in fluid property inside your flow system due to the coexistence of different layers with different properties. Okay. Now, two different type of actually example I have given here. One I have named as channel flow and another one free surface flow. In broad way, you can tell like one is completely bounded flow, another is open flow or semi-bounded flow. So first one is from engineering example, engineering example, that primary cementing process, where you can see coexistence of different layers inside the channel, and due to coexistence of different layer with different properties, there can have a stratification process inside the system. And the next one is actually tear film structure, which is a thin film flow. Already Professor Usha discussed actually in details about the thin films. But in her discussions, he has considered only single layer film. But in tear film structure, although it is a very thin film, inside a tear film, there is different layers with different properties. So there is coexistence of 3 to 4 layers inside a tear film, and that's why it is also a stratified layer. So next, if say we have a stratified system, or say viscosity stratification inside your flow system, then as per my earlier slide, we can classify the flow systems in two broad categories, like channel flows and free surface flows. Now, for time being, let's say we are interested in channel flows. So let us first understand how stratification process occurs inside a channel flow and how we can classify different kind of stratified flows. So that stratification, as I told, stratification can occur due to the coexistence of different layers or due to the change in properties by some other effects. Okay. So if you see figure 1, then you can understand that there is two different fluid 1 and fluid 2, and say they are immiscible in nature. Their viscosity, density, as well as other properties are completely different, and that's why they cannot mixed up with each other. And between these two fluids, then there can exist one sharp interface. So this kind of flow system is known as interface dominated flow. So like say you are considering water and oil together inside a pipeline. So in that case, it can be think about that it is a interface dominated immiscible flow system. And in this case, fluid properties are usually expressed in terms of step kind of function. So this particular function is a step kind of function, and so you have to actually take proper care in the interface to do the analysis of this kind of flow. Now the next type of flow, if you see figure 2, I have given one non-Newtonian fluid system where you can see that fluid properties can continuously change from one boundary to another boundary, and it can be represented by a linear function or continuous non-linear function. And this is nothing but this is non-Newtonian kind of flow like blood flow, etc. But if you see the third class of channel flow system where actually more than one fluid coexist inside a channel like fluid 1 and fluid 2. However, these two fluids have a new actually phenomena, that is they can mixed up to each other, mixed up, and they can create a new layer in between the two layers, fluid 1 and fluid 2, like say hot water and cold water, or say salty water and fresh water. If such kind of combination you are taking inside a channel, then what will happen? Due to the diffusion process, there is some scalars, like say this salt effect or temperature effect, etc. So though due to the diffusion process between the two layers, that interface, sharp interface will diffuse, and it will create one intermediate layer or stratified layer or mixed layer in between two fluids. And in such cases, you can take help of again one continuous function, but that continuous function is a different type of function. That function is constant in fluid layer 1, that function is constant in fluid layer 2, but it can continuously vary in the diffusive layer. And you can take such kind of function to represent the fluid properties in the miscible flow system. So the third flow system is known as stratified flow system or miscible flow system. Okay, and our interest is to study the class 3 problem, because already there are lot of studies on class 1 and class 2 problems, and now we actually interested to explore that what are the different results corresponding to the class 3 problems. So again, the two different motivation, we have solved few problems related to class 3, and depending on the two different motivation. The first motivation is what are the effects of miscibility in the instability of such kind of flow, and the next one is what are the effects of boundary sleeve or wall sleeve or on the instability of such flow systems. And why actually we are considering that? Because there are different works, experimental works as well as theoretical work, which tells us that if the fluids are miscible in nature, or there exist certain scalars or certain species inside the flow system which can diffuse inside the flow system, in that case your interface between two fluid will be diffusive in nature, and therefore there will be a diffusive layer between the two fluid layer, and that diffusive layer can have a certain thickness, although it can be its thickness modulus will be less as compared to the thickness of the fluid layers, but it can have a finite thickness, and that's why we should consider the stratified layer between the two miscible fluids. And next one is why actually we want to consider that this wall sleeve effect, because when you are considering one channel or any other kind of flow, walls are not always completely rigid, and that's why your velocity, fluid velocity, will not be completely zero at the wall. There will be certain finite velocity near the wall, and which is known as partial sleeve. So we want to actually apply two things, miscibility nature and wall sleeve effect, in our study to understand the instability behavior of third kind of flow system, and we shall actually check how different effects like miscibility effects and wall sleeve effect can control these instabilities. So now quickly I want to give little bit brief idea about the flow instability, how actually we can capture flow instability inside a system. So in any flow system, to capture the flow instability, first actually we have to solve the equilibrium state or base state system where there is no perturbations. So at the initial stage, we have to solve the problem, and that will give us the base flow solution or equilibrium solution. After that, we can introduce certain amount of perturbation. It should be a small perturbation since we are interested in linear theory. So if we give certain disturbance or perturbation in that base solution, then your system will be perturbed and behavior of the system will change. Next, we want to find out actually solution of the perturbed stage as the combination of base stage and the perturbation stage. So in this way, actually, we can solve the problem to capture the instability. However, depending on the behavior of the perturbations. So in this case, actually, perturbations are, we can think that perturbations are some waves. You are giving certain waves, and those waves can change their amplitude with respect to time or with respect to space, or it can be change its amplitude with respect to time and space both. So if actually perturbation are changing with respect to time only, then that is temporal instability. If they are changing with respect to space, then we can have spatial instability. And if it is changing its amplitude and behavior with respect to space and time both, then it can be spatio-temporal behavior. So first two figure gives the idea about the temporal change of the waves, and second last two figure gives actually idea about spatial change of the perturbations. So little bit more if I talk about that solution of the perturbed system, or say instability of the perturbed system, then what actually we are doing, first we have to start with governing equation of your problem. Appropriately, you can do the non-dimensionalization, because then you don't have to take headache of units and you can apply your model to any scale. Then you have to find the base solution, as I told, which I have denoted by U bar. And finally, if you put some infinitesimal perturbations or small perturbations, then your new variable U is the combination of, or new solution, flow solution U, which can be think as velocity, which is combination of two things, base flow solution and the perturbation. So small u represent the perturbation part. That means some correction you are doing in your equilibrium solution or base flow solution to obtain the solution for the perturbation state. And that same thing I have given in figure form. So actually we want to obtain the graph of or velocity profile of figure 1, which is the velocity for the perturbation flow or perturbed flow. And this is nothing but combination of two things, like mean flow, which is a parabolic profile in blue color, and say there is some fluctuation or perturbation, which is given in red color. So if you take the combination of both the things, then you can get the resultant flow like this capital Uy, which is U bar plus U. So again, if we try to understand the mathematical things, how to solve this instability problem, then in a very simple way, we have to understand that our perturbations, a package of perturbations or disturbance, can be sum of certain types of waves. So it can be sinusoidal, it can be cosine wave, or it can be sum of different type of waves. And this idea tells us we can think that our perturbations of some Fourier modes. So different modes with different amplitudes and wave speed. So finally, our inside a perturbed flow, we can have different waves, perturbation waves. And that's why the general perturbation, we can think about that sum of different perturbations. And so we have to move, before solving our problem, we have to move the original space, like temperature and spatial direction space, to our wave number frequency space. Okay, then we can understand the behavior of the waves. So to do that, what we have to do, we have to use actually Fourier transformation as well as Laplace transformation back to back, to transform the variables from xt to alpha and omega. and another variable, spatial variable, y will be as it is. And in this process, what will happen, we can actually transform our partial differential equations, because whenever we are considering a complicated flow system, we have a coupled Navier-Stokes equations, which is highly nonlinear, and many variables are there. So to actually transform our governing equation to simple equation like ordinary differential equation, we can take help of this Fourier transformation as well as Laplace transformation together, and that will give us two new parameters, alpha and omega, and only one spatial variable y. So this process actually known as also that normal mode solution process. So using normal mode solution, we are interested to capture wave-like solution inside the system, and those normal mode solution can have two different part, like amplitude part, which is given by this u cap of y, and there is exponential part, that means amplitude part and wave part. So wave part actually modulus of the wave part is fixed, but amplitude part dependent on the spatial coordinate y, and it will change. So here, as I told, we have two different parameters in this process, that is alpha and omega, where alpha is called wave number and omega is known as frequency. And as I told, that this process will convert your PDEs to ODEs, and as you know that the system of ODEs or simple ODEs, solving ODEs is much more easier than PDEs. So with this idea, now actually we can define our definition for instability, like temporal and spatiotemporal or spatial instability. If you see the exponential part, this actually perturbations exponentially dependent in space and time, and there are certain coefficient for time t and space x. So depending on those coefficients, you can actually conclude that perturbations can grow, perturbations can decay, or it can be neutral. So if we take that our omega parameter, which is frequency, and it is coefficient of time. So depending on omega I, if omega is less than 0, then obviously your perturbations will not grow with respect to time, it will decay, and therefore you can get temporal stability. But if omega is greater than 0, then your perturbation will grow with respect to time, and then you can get your temporal instability. However, in the case of omega equals to 0, no change will happen with respect to time, so it will be neutrally stable. And similar way, you can define for spatial instability as well as spatiotemporal instability. So now time to discuss about different configuration of stratified flow, which we have considered earlier and we have solved the problem. So first two figures are known as like single component flow and double diffusive flow. What is single component flow? If say we have a flow system with two different fluids, in the core region one fluid and in the outer region another fluid, and there is a species called say S. It can be temperature, it can be salt, it can be some other species which has diffusivity property, and this diffusion rate is different in two different fluids. So then in between two different fluid, you can have a mixed region due to the diffusion process, and since the diffusion process is happening due to presence of only one species, you can name this type of problem as single component problem, and this is a stratified problem. Now next, if you consider that there are two species like S and F, one is faster and another is slower diffusing species. So in that case, again you can have a mixed region in between two fluid system, but since two different species are diffusing inside the flow system, so you can name this system as a double diffusive system or DD system. And the below two figures are nothing but similar kind of system, but with a free surface. If you are considering a falling film of two different liquid which are miscible in nature, then you can get a configuration like figure C. And the third one actually gives that that same kind of figure, but where we can give the inviscid analysis. All other problem we have done the viscous analysis, but in the fourth problem we have done a inviscid analysis. So I want to discuss this viscous analysis part, and if time permits, then a little bit I will discuss about the inviscid analysis part as well. So now actually if you quickly see that governing equation, again that Navier-Stokes equation, so it can be channel flow, it can be free surface flow, just you have to include the body force term in the case of free surface flow. However, since we are considering viscosity stratified flows due to the presence of diffusive species, so here your mu is function of the properties of species, and that's why mu is not a constant here. And there are two different transport equations corresponding to two different species. So scalar transport equation, convection diffusion type equations, which is given for component S as well as component T. Now to actually solve this problem, we can assign appropriate boundary conditions. Now as I told, we are interested in slippery channel flow, and that's why we have to take mixed type boundary condition, which is also known as Navier slip boundary conditions, so which is included here. And if you are considering symmetry inside your channel, that means you want to analyze the things in a half channel, and your flow system is actually symmetric with respect to center line, then you can apply symmetry condition or this no stress jump condition at the middle. And in the case of free surface, what you can take the free surface conditions. Those and free surface conditions have three parts. It is combination of kinematic condition, which actually gives us the deformation of the free surface, and another two things like stress jump, normal stress, and shear stress, how they are actually changing at the free surface, that can be captured or that can be given in terms of shear stress balance and normal stress balance. So therefore, depending on your flow geometry, you have to actually take your appropriate boundary conditions. So as I discussed, yeah.
Sorry to bother. So can we just have 5 more minutes and have little question answer?
Yes, sure. Okay. 5 to 7 minutes I need just.
Okay, sure. Thank you.
Okay, so now from this governing equation, next part is you have to actually find out your perturbation equations. So to find out the perturbation equation, you have to actually choose the variables, which is combination of base flow and perturbations, and then simplify it. If you remove the non-linear terms with respect to perturbation, then we can end up with a linear system in perturbations. However, these are again coupled equation and set of equations, and in linear stability theory we can take help of Orr-Sommerfeld analysis to actually capture the instability in much easier way, and that's why you have to calculate the stability equation, which is known as Orr-Sommerfeld equation, after applying the normal modes, and these equations actually given here. So this is the complicated Orr-Sommerfeld system for stratified flows. Here many terms are there, and that's why it is known as generalized Orr-Sommerfeld equation. So in basic Orr-Sommerfeld equation, there will be very less term, but here due to the existence of viscosity stratification and viscosity perturbation, many extra terms are there. So to solve, actually you can either try with the analytical approach and numerical approach. So analytical approach, like already Professor Usha mentioned, you can take help of long wave analysis, with which is nothing but one kind of Taylor series expansion, or weighted residual method, etc. However, since these type of problems are complicated, it is not easy to implement the analytical methods. You have to go through numerical process, and the Chebyshev spectral collocation method is the most used and most appropriate method to solve these kind of problems, where what we do, actually we convert our flow domain to the domain -1 to 1, Chebyshev means domain, to take help of the orthogonality property of Chebyshev polynomials. And we discretize the domain with help of Chebyshev collocation points, which are equally spaced point. And what we do, we actually approximate the flow variables in terms of series solution or in terms of finite series of Chebyshev polynomials. And if we satisfy our equations or this solution at each point, then we can end up with a set of linear equation, which is nothing but a matrix eigenvalue problem, which is generalized form is given here: a into x equals to c into bx, where x actually is the eigenfunction and c is the eigenvalue. So if you solve for x, then you can get the flow variables, and if you find out the eigenvalues, then based on the eigenvalues you can track out the instability behavior. Here few numerical results I have given corresponding to single component SC flow as well as double diffusive flow. So in the case of SC flow, we have plotted the neutral stability boundaries. That means on these curves, actually your flow system is neutrally stable, omega I is 0. Inside these curves, your flow system is unstable due to omega I greater than 0, and outside it is stable. So if you see, then as compared to your simple plain Poiseuille flow, when you are considering the same channel flow with a diffusion process or with a miscible process, then you are getting three different unstable regions. And this is occurring due to different unstable mode, like this overlap mode, interface mode, and then shear mode, etc. Also, we have actually captured the effect of wall velocity slip. Wall velocity slip parameter is nothing but this beta, and we could see that wall velocity slip can have a great control on these instabilities by stabilizing the overlap mode, because that is the most dangerous one. It is occurring at very small Reynolds number. So RE is the Reynolds number. It is occurring at very small Reynolds number. So this is the dangerous one. And wall velocity slip can stabilize this kind of dangerous mode. These figures we have these figures are related to double diffusive system. In the case of double diffusive system, again, actually it's depend on different flow parameters. All double diffusive systems are not unstable. A certain combination of actually log mobility ratio inside the flow system can give you a instability, and once the flow system is unstable, you can capture different kind of instability again. So here this DD means double diffusive mode, which is usually occurring due to the presence of diffusing species and the mixed layer. So again, we could see that if you apply the wall velocity slip on this flow system, then you can stabilize the most unstable mode, which is the double diffusive mode, by decreasing the unstable region as well as unstable wave numbers. So now just I want to discuss the final thing, like say there are different type of instability. Like in the case of single component flow, one kind of instability; in the double diffusive flow, another kind of instability. So from where those instability are occurring? What are the physical mechanisms behind that? If you want to capture that, then you have to actually do the energy budget analysis corresponding to the pattern flow. And after doing the energy budget analysis, you can get the contribution of different terms inside your flow system, pattern flow system. And after analyzing those things, we could understand that normal component of viscosity perturbation plays a great role to introduce instability at low Reynolds number. So similarly, you can actually explore this process for different flow system to get the physical mechanisms. Again, just you can study absolute and convective instability inside those flow systems. If you actually, instead of taking the general perturbations, if you take that standing perturbations or the traveling perturbations, then you can obtain the behavior of the instability in terms of absolute instability and convective instability. And in this case, what you have to capture? You have to actually capture the absolute frequency. And to do that, what you have to do? You have to take spatiotemporal perturbations and spatiotemporal instability process. Few figures are given here related to absolute instability, and in these figures actually the contours are nothing but contours of absolute frequency, which is omega I. We have drawn in the alpha, that real alpha and imaginary alpha plane, that means complex alpha plane. And if you track out the saddle point, that is this middle points at each case, then at the saddle point you have to check the behavior of the absolute frequency omega I, and depending on the positive and negative value you can judge that that system is absolutely unstable or not. And the conclusion is double diffusive flow system is relatively more absolutely unstable as compared to the single component system. So as there is time shortage, so I am not going details about this open flows. So in the case of open flows, in similar way you can design the Orr-Sommerfeld system and you can apply the boundary conditions to obtain the results. And these results are given here. Again, the conclusion is in the case of free surface flow, if you are taking miscible system, then miscible system is much unstable than the single or say fundamental free surface flows. Okay, and in this case again that slip parameter has a great control in the instabilities. So with this I'm actually finishing today's talk, and if you have any questions then you can please go ahead.
Thank you, Sukhendu, for this nice and detailed talk. I'm sure the audience might have got some idea about stability, the basics part. So for the shortage of time, we'll just possibly take one quick question. So if there is any question from the audience, they can directly ask to Sukhendu.
Good evening, sir. One question from my side.
Yeah, please go ahead.
Sir,
Yeah.
question is that why we will we take only normal mode perturbation? Any other perturbation is
Yeah, so why actually we are considering that already I have discussed. So here actually whenever we are giving a perturbation to a system, like say if you are considering a glass of water and you are giving a say disturbance on the glass, then usually that perturbation, what it will create some waves on the top of the waters. Or if you are throwing say one stone in a pond, then again if you remember that you will see that there are certain waves. So since our perturbations are wave like, so that's why what we are thinking that our perturbations have some amplitude and there is some wave part. And another thing is this normal mode actually perturbation help us to convert our equation from the complicated PDEs to the simple ODEs, which is Orr-Sommerfeld system. It is not simple, but it is much easier to solve than the full Navier-Stokes system. And this is one kind of separation of variable process, nothing else.
okay. Thank you, sir.
Thank you, Sukhendu. And due to shortage of time, we have to stop here. But if you have questions, feel free to directly write to the speaker or let us know so that we will help you to get connected. Thank you, Sukhendu.
So thank you so much, Satyajit and Vikas. And okay, so maybe I can discuss some more problems in next symposium.